recorded. Yes, thank you. Right, okay, here we go. Right, so you should be able to see my browser right now. So here's the brief things I wanted to say about assignments. So as for assignment 1, if people's regret requests are being processed as they come in and requests are open for another week, if people really feel that their requests are not addressed by Gradescope, for example, if the reply tutor denied your comment but didn't give an explanation, you can always reopen the request. And right, I just honestly say that we cannot handle separate email, Piazza, and Gradescope requests that are not linked to each other. We basically can't do that in order to spend the most amount of time like helping people, which is looking at what the request is rather than keeping track of where the requests are. So I will open a separate Piazza thread. Basically, people who have requests that can't be handled via Gradescope, for example, AutoGrader, some AutoGrader requests can't be handled directly in Gradescope, then post a note there. Yeah, so that's that. Assignment 2 is released. Expect some updates in the next week or so that will not change the question or what's asked of you, but we will provide some help in auto grading, give you some access to in Gradescope about, for example, checking the size of your output, so that you can avoid simple problems that makes AutoGrader unhappy. So video assignments will be out later this week. So the main content that I wanted to chat about is assignment 2, of course. Once you sort of unzip the release, this should be the directory structure you're seeing. Let me just walk through. So the data folder basically contains some resources for question 1 and 3. Question 1 contains, for example, pre-specified conditional probability tables, and then sample data set. In question 3, it contains the data set and also some meta information about the data set, such as genre and movie name and so on, which you will need later on. Framework basically contains the support code of question 3. Don't change it. But different parts of the question do require you to read some of it, and we believe it's useful. I believe submission extras is, yes, it's empty, but if you would like to, for example, include any images with your submission, this is the place for it to live. And package submissions, script basically gives you, yes, it's basically a script that zips your 3 IPython notebook files and the submission, anything under submission extra, and ignores everything else so that you can upload these to Gradescope. README.md is basically a high-level statement of what the questions are. So as I said, there are 3 questions to complete. It asks you, here's how you submit. And there are some do's and don'ts. We will spend most of our time today talking about each of these questions and what they are intended, sort of what you're expected to understand out of the course in order to do these questions. Right. So as mentioned in the last workshop, you can't really do a Bayes network yet unless you've read ahead in the book and the course content, but we will start covering that part end of next week. So after kernels and sampling, we will start covering Bayes networks. And then you already know the EM part. You can already very well do kernel PCA and the recommender systems using autoencoder question. So I'll walk through the base net, or like walk through the 3 questions sort of in turn, and you can always revisit when you're ready to do question 1. So in short, Bayes network are a way of encoding dependencies between random variables. Some of them are observed, some of them are hidden. Where hidden simply means, for example, you've seen EM, the cluster membership is not observed. So in this question, you are working through a toy network, which is not real. So we cooked it up to basically try and perpetuate a few phenomena that's prominent in Bayes nets. So there are 10 variables, I believe I did work through this, yes, 10 variables. Each of them takes a discrete number of distinct values. So here is some supporting code. It asks you do not change it, right? So the dependencies between these variables are specified in this chunk of code, which you are supposed to read. And then you need to draw the Bayes network structure for the network defined above. And correspondingly, because the conditional dependency is specified, you're asked to essentially write out using Bayes, we'll write out the joint distribution as factorized as above. So these should be easy once we are through the first Bayes network lecture. And then just to, I guess, condition people's thinking, calculate the number of parameters needed with this factorized joint distribution versus if the distribution is not factorized, if we're doing the full join of the 10 discrete variables, how many parameters we need. Right. And that question 1.2 is to use essentially Bayes network structure to reason about the conditional independence. Basically, the argument there is variable 1 and variable 2 independent given another variable or another set of variables. There are recipes for this. So part 2 and 3 are the main parts. So part 1 is a warm-up. The part 2 basically asks us to learn variables that more or less does not depend on the later variable, which is the aptitude. Right, so this scenario is basically people have aptitude, they have test scores, and they may or may not get a job. And there are observations we can make, such as how much mark people get in the exam and whether people attend tutorials. So don't take this, I guess, the specified dependencies too seriously. It's just mainly for like our mental exercise. But aptitude is something that we claim that we do not observe, but we could possibly infer from these grades and interviews and attendance and so on, right? So there are, so in this 10 variable network, there are conditional dependencies where we can infer from the data without sort of relying on the aptitude. First, this question asks you what they are, and then it asks you to write out the code that does the inference, right? So there's a bit of a notation which this bit handholds you through, and you're supposed to essentially write out the maximum likelihood estimate of these conditional distributions and then implement it. Of course, you can also check them, right, using what's known from the rest of the class. And the inference is made on the set of basically the same data set of a hypothetical 5,000 data entries, right? In reality, it's hard to get 5,000 student records to actually do this, but here we use that because the data is synthetically generated. Right. The next question asks us to essentially work out how to train this latent variable model, basically estimate all the parameters in the space network using the EM algorithm, given the latent, like taking into account the latent variable A, right? So we have, so there's a bit of a new notation. Basically, x's are the observed variable, z's are like refer to the latent variable, in this case, just one of the 10 variables. And then you're supposed to work out how to estimate them. There is the recipe being given here. And then you can run your EM algorithm and see what it gives you. Part number 3 is another part where, given a learned model with latent variables, can we make some inference? For example, right, you can say, oh, if a student scores highly in tests and attends our tutorials, how likely they'll get a job, right? So the inference task is framed around inferring marginal distributions of the subset of variables. And then you will be held responsible, right? Basically, some of the functions you write in here, as with the rest of the assignment, are going to be put into an auto testing environment to check what they are. So the intention of the testing is that you can develop and debug your algorithm on a 5,000 toy data set, 5,000 entry toy data set, and the auto grading or testing will be done on a slightly different data set and potentially slightly different set of underlying model parameters. So what the overall intention of this this part is to give you some first-hand experience with Bayesian networks of a given structure. Learning Bayes network dependencies is another whole different sort of difficult problem. But given dependencies, being able to make like parameter estimates and inference is the core skills that you should confidently walk away from this class. Okay, so that's question 1. Any questions from you guys so far? Oh. Okay, so if not, let's talk about the next question, kernel PCA. Okay, so we are learning kernels right now if you're going with the workshop schedule, and also principal component analysis. We covered that a few weeks ago. So here we look at how we can essentially marry the two ideas. So in the book, there are 2 sections that's relevant to this content. One is dedicated to kernel PCA 12.3, and then the other one, 12.1.4, is basically discussing what happens if we have more dimensions in the data than number of data points, right? So the gist of these 2 sections, and the first question is, what is the relationship between the eigenvalues and eigenvectors of the kernel matrix, which is n by n, as opposed to the covariance matrix of feature functions or a kernel basis functions, which is d by d. So, right. The spoiler here is if there is a non-zero eigenvalue in one, it is actually a non-zero eigenvalue in the other as well. Because n and d are different, the number of zeros they have will be different. So this is, I guess, a warm-up for your linear algebra. You may wonder why we're asking this. Given the 2 sections, I can tell you that the normalization across these different sections and what's presented here is slightly different. I believe in this question, you can essentially derive a simpler, mathematical expression as far as normalization is concerned. So you just, if you have digested these 2 sections, you should have no problem. In the second section, you're going to turn these linear algebra into code. What this does. Does it show us the data? Maybe not. Or maybe it actually lets me run it. Let me see. So it first includes some data for generating a synthetic data set of 3 concentric circles colored red, green, and blue, if my memory serves me correct. I think my computer is really slow because it's trying hard to record a video. Right, so here you go. Without doing anything, you can already run the 3 cells. And this is the toy data you will be looking at. And the next part of the question asks you to use this 3rd order polynomial kernel and essentially perform PCA, kernel PCA with this kernel, right? And then it asks you to, so the first question here, for example, asks you to actually first expand this polynomial kernel into its basis function, which is, we've seen an example of doing so for quadratic kernels, and we talked about it last Friday. You should be able to do, and then implement in code. Because this data set is small, in here you don't have to worry too much about efficiency. You can just call whichever eigenvector function, eigenvalue function that you are comfortable with. Yeah, check your results and plot your data and see what the projected data look like. The idea is, well, the clusters are not linearly separable here. Are they going to be, basically, are the 3 colors going to fall into like exactly like 3 lumps that we can clearly separate after kernel PCA? You can decide after you do this. Right, then the next question, 2.4, asks you to essentially do the same thing, but project the data using the RBF kernel with a given gamma. And then you're going to write your code, but turns out that this particular choice of gamma is probably not great. And it asks you to find a different gamma and run the same code again. And that's, hopefully you can find a gamma where the projected data is linearly separable. And hopefully you would have reasoned for yourself why the choice of gamma is good that way. All right, so that's essentially question 2. And now let's look at question 3. As hinted in one of the workshops, we briefly covered autorec in the workshop. If you have gone through that, that might have been the lecture that wasn't recorded. Okay, but in short, there's this 2-page paper that specify a simple architecture and objective function that does recommender systems using autoencoder, right? It's also not a deep learning system per se. The reason we choose this paper is not just because I know this paper fairly well, being one of the authors. It turns out this paper, despite it's really simple, it's one of the first papers that uses neural networks to do recommender systems. It wasn't the right. At that time, there was another paper by CMU and Toronto team on using restricted Boltzmann machines. That was what this paper compared with. But nowadays, this particular paper has made its way into the Kevin Murphy's new version of machine learning textbook coming out this year, and also another recommender systems textbook by Alex Smola and his collaborators that came out last year. So we were, as authors, we were pleased to see that. And for this particular class, we thought it will be nice for you guys to essentially follow a like new but simple approach And try your hands on recommender systems, which is a topic that we did not delve in depth in this class. Okay, so, and for those of you who are interested in a research project, some of your study program kind of requires it as well. Reproducing, for example, a state-of-the-art paper is usually the very first step of your research project. It's not necessarily an easy step though, but we hope that this well, the educational goal for this particular question in the assignment is to help you do that. After this, you would have been sort of helped through once for reproducing a paper, right? Okay, so one open secret that's not talked a lot in machine learning textbooks, but in machine learning research groups that most groups knows that if you wanted to do research in an area, you need to learn how to generate synthetic data. This exercise is no exception, right? So we did that twice in question 1 and 2 already. In here, there's some synthetic data being generated for you with 10,000 points or, okay, I'm actually not sure what this particular cell, right. And you can explore the synthetic data about, for example, what dimensionality and what ranges and how many data points. So you should, yeah, go ahead and do that. Right, the other fundamental skill for machine learning research is to understand your data, right, before you try and generate accuracy and loss metrics on them. So because data is synthetic, the data is actually complete. Although the recommendation system's problem essentially is a data completion or imputation task, where we have some rows and then there are missing entries. So in here, you're going to make a function that masks out some entries so that we can reserve them for testing. So that's task number 1. It's a warm-up task. Hopefully if you like, basically it also helps you to sort of get your heads into the NumPy array that we'll be working with. After you get that right, you are going to make an autoencoder, right, with a forward function, backward function, and then right, make the encoder and decoder and make it able to recommend a rating or recommend a value for the unobserved entry. And here is the autorec function. So the G part, so the input is a vector is called R. V times R plus mu is the passing through a G function is the encoder, so this part is the encoder. And the outside part, as you can see, has exactly the same format. It's basically W times this encoded vector plus another bias term B is the decoded function, right? So this is just on the both stages of the autoencoder written in one equation. There are some utilities implemented for you, right? So the sequential class will batch your data and then apply them, right? So if you, and it will take basically individual functions, and then it's a sequential of f, g, and h will basically output the composition of these functions. You are to basically implement the loss function here. And also the regularization is given to you. So we now are ready to train the recommender system on the synthetic data and observe what happens. You're also going to plot out the synthetic data. Yeah. So well, don't change the random seed, and then we can basically visually check where your results are correct or not during gradient. You're going to write some code to explore the latent space, basically the encoded vectors in the middle of autoencoders. So just as a reminder, let me try and pull out what that means for you. Might be week 6a. Okay, it's better to go back to quickly browse the already annotated notes. Okay, this was the PCA, right? Okay, week 5b sounds like it. Let's see. Yes. Okay, so here's the autoencode. All right, it wasn't shared. Wait a sec. Let me reshare my screen. Okay, I'm just sharing the whole screen right now. Right, so this is the picture of the autoencoder. There's input, nonlinearity. In here, there's only one layer. Let me just scroll down to the right place. We're not dealing with stacking autoencoders. Yes, so here. So what happens here is basically, right, at the end, the synthetic, the real data is matrices like this. There's this big R matrix with R's as row vectors or column vectors, and there are missing entries. So in the autoencoder, the input is at the bottom with missing entries. And then the latent space you will learn is these blue dots. And we can examine them. Well, for example, take 2 dimensions and plot them out. For the real data, I don't actually recommend plotting out the first 2 dimensions because the latent dimensions are usually redundant. And from the paper, there's 400 of them, right? And then the output is basically the same dimension as the input. Also note that the objective at the missing entries are essentially zeroed out when you do training. So it's up to you to do that. Another thing that's worth noticing is that according to the paper, at least for the movie lens data set, the real data item-based recommendation is better for auto-rec. Basically, in this, let's say, user item matrix, we take row or columns as data vectors that we feed to like this autoencoder rather than rows. Like in most of this class, we make a data matrix and each row is a transpose of the data vector. In here, we take columns. The high-level understanding why this works better is because we think for each user, the data is more sparse than for each item. Basically, if it's a movie, it's sort of taken a significant effort and budget to make. There is at least a few users who have watched it. But for a user, the watch history might sort of reflect the user's true interests less well, right? So we feel that the broader comment is that what's called a cold start problem. Basically, when you have a user that has no history or a brand new movie that nobody has watched it, recommending good users or items to watch in these cold start settings is always very challenging. This particular exercise and paper does not tackle that challenge, so to speak. We're just picking item vectors for which the cold start problem is not as much of a pain, essentially, right? So this is basically what like the result evaluation in the paper look like. We're also going to just recommend you guys to adopt the setting of, for example, there's f and g function that can potentially be nonlinear here. For the g function, we recommend the sigmoid, and then for the f function, take the identity, basically linear activation. Yeah, you don't need to, once the paper has experimented all of these, you don't need to like essentially experiment. But if you like to and have spare time to do so, feel free. In this, now we go back to the assignment question. Right, basically we can plot out the latent space in synthetic data. It should make some sense. There is a geometric shape. When we make the synthetic data, and it should come out. It's not like one of the simple shapes, but you should see something, right? Right, in the next section, you're going to work with this movie lens data set, which is the smallest of all real-world data sets. You are going to implement simple functions that allows you to look up the information about movies given the data, like for example, given the movie ID, provide a name and genre and so on. This is important for interpreting your result, and you're also going to be auto-graded based on this. So yeah, to make it worth your while doing this. Right, so you are going to initialize the recommender engine for this. You're going to train it, and you are going to be asked to provide recommendation for user 42, print out the top few movie or the top one movie recommended for that user. And then you're going to examine whether that result follows the training data and so on. Right, so that's the end of the recommender systems homework. And that's also the end of what I have to say. Is there any questions so far?
Hi, Leshing. I'm wondering what is which is the centralized Piazza thread for assignment questions, especially when it comes to the autograder?
I will make one right after this, I will say.
Okay, thank you.
Yeah, and after that, I might post a number in the Teams, basically below this meeting.
Cool, thanks.
Yes. Okay. So if there's no questions, yeah, have fun with your assignment too.
May I ask,
Yeah.
is there any other place we need to add a random seed? As you mentioned, the random seed need to be added, but from the code I've seen there's place already specified the random seed with the seed value. So is there any other particular place we need to add a random seed?
I would say no, but let me check that answer with we made this as a team. I would recommend when it has a seed, don't change it. The auto grader may actually change the seed in order to test your code, right?
Yeah, of course.
Yeah.
Yeah, definitely. But just would like to ask if there's other particular place that we need to add a random seed and a seed value, which I think shouldn't be the case, right? But just would like to confirm as you already specify in the in the requirement. This is one of the critical kind of session.
Yeah, I believe the answer is no, but I'm taking a note. Basically, if if I find out otherwise, I will announce it on Piazza. And the way we announce updates on clarifications like this is basically below the same thread of assignment 2.
I'm sure the other question is so we got a, let's say, from the task the question 1, we need to write the relationship of the nodes and for the Bayesian network, right? So if we write on a piece of paper, then scan as PDF, could we just attach into the session a particular session of the question, then we also add a PDF file in the actual work, then got zipped together? Will that sufficient?
Good question, right? So the way I recommend you to do this is that you need to make that picture appear in the box on my screen right now. If you know what I mean, right? So I believe IPython Notebook takes a picture. Let's say convert your PDF to PNG, and then you can basically tell the notebook to find this PNG file and show it here. And of course, include that PNG file in your submission extras directory.
Sure.
Yeah. I'm not sure it will show PDF here, but I'm pretty sure it does show images. You can try. Okay. Yep, that's it then. Enjoy your week, and I'll see some of you on Friday.